Greetings, Astronomy 10. Welcome back to your lecture series. We're going to be starting with chapter 14 today. That is galaxies. A galaxy is a gravitationally bound group of stars. Our galaxy, the Milky Way, contains something like 100 billion stars. That's a whole lot of stars. It's quite large. From one end of the spiral arm region to the other, it's about 100,000 light years across. It's so large, in fact, that once upon a time, actually less than 100 years ago, people used to think that the entire universe was inside our own Milky Way galaxy. In 1920, two astronomers named Curtis and Shapley presented their arguments in what would be known as the Great Debate. At the time, we did not, back then in the 1920s, we didn't know what the limits of the Milky Way were. We didn't know how big it actually was. And as we'll see in the future, that was kind of a shocker. But it was the subject of much speculation. Lots of people had ideas about how big the universe actually was. Lots of people thought that there were other spiral nebulae outside of the Milky Way. These things that now we know are actually galaxies, like the Andromeda Galaxy. Citing that there were lots of these nova events that we now know to be type 1a supernovas and standard candles, things like that. But they had this debate, and no one was able to present conclusive arguments because, long story short, they were both wrong. And about a year later, someone named Edwin Hubble, an astronomer, figured out the answer. And if you look at the third image in today's image bank, he wrote directly on the photographic plate what the answer is. There's a picture of two of them, two of these plates, and you can see up in the upper right-hand corner of the image to the right, he wrote in red right on there what the answer is. Now, back then, we didn't have the same kind of sophisticated technology that we have now. Nowadays, we have CCD, or charge coupled device cameras. You know, it's like the ones that we use in our phones or whatever. Everything's all electronic. We had big, huge telescopes and whatever. But back then, they had telescopes that weren't as sophisticated. They didn't have, adaptive optics and all this other stuff. They didn't have telescopes that were out in space, that didn't have to compete with our atmosphere. And in order to take images, they couldn't just take the image and burn it to the hard drive, and he couldn't just store it, in a bunch of magnetic characters on a hard drive like we do now, right? And so what they did is they would take pictures on photographic plates. And I think back then, don't quote me on this, but I think the cost back then was something like $100 per plate. And adjusted for 1920s dollars, excuse me, that was 100 years ago, and so that was thousands of dollars. And the legend goes that when Edwin Hubble was looking at these two plates in what we now know as the Andromeda Galaxy, he was so excited with his discovery that he wrote directly on the plate, which back then that was like a huge no-no. Because, it cost thousands of dollars for just one of these images on this photographic plate. So what did he see? What does it say up there in red? I know it's tempting. Everybody, every semester, there's always someone who says war. Huh. A little Edwin Starr reference for you there. But no, it doesn't say war, it says VAR, and he wrote an exclamation point next to it. And you actually already know the answer. He found a variable star. likely a Cepheid variable star, in the Andromeda Galaxy. And because there's this period luminosity relationship for variable stars, he was able to determine what the luminosity of the star was, and then comparing it to its apparent magnitude, figure out how far it actually is from us. And as a result of figuring out that the Andromeda Galaxy is something like, a million light years from us, they realized that the Andromeda Galaxy had to be far outside of the Milky Way. So now we know that there are tons of galaxies in the universe, right? That we're not alone, we're not the only one. Even Einstein fell prey to this kind of goofy geocentric thinking that we're the only galaxy in the universe, right? We're not even in a special place in our own galaxy, much less the only galaxy in the universe. But first things first. The Andromeda Galaxy kind of looks like ours. And back then we didn't know what our own galaxy looked like so much, right? You can't exactly see the structure of the Milky Way from inside the Milky Way very easily. And so that begs the question, even though now we know that the Milky Way is a spiral-armed galaxy, like the Andromeda Galaxy, are all galaxies the same? Well, why would they be, right? Sure, there's this thing called the cosmological principle that says the laws of physics are the same everywhere. But that doesn't mean that the universe is exactly the same everywhere, right? Ever seen a cat? Well, is the universe made of cats? No, things are different in different places, right? But space-time is everywhere, and so the laws of physics permeate the universe. In any case, there are tons of different types of galaxies, and if you look at the next several images in today's image bank, there's a nice spiral arm galaxy. There's a spiral galaxy that has like a bar structure across it. And that's actually what the Milky Way looks like, right? We're a barred spiral galaxy. There's one that kind of just looks like a round shape, call that an elliptical galaxy. And there's one that kind of has, I don't know what's up with Ninja, I guess it's playtime. In any case, there's a galaxy that doesn't have any real kind of set shape, right? That one kind of looks like a jellyfish or something. Ninja. What's the matter? Come here. Okay. Where are you going? Ninja. What's the matter? It's bath time now. Cats are so weird. In any case, spiral arm galaxies all have spiral arm structures, right? Barred spiral galaxies have a bar across their center, across their middle. Elliptical galaxies don't have like a disk that there are spiral arms in, and so they have more like an elliptical shape, more three-dimensional than two-dimensional. And irregular galaxies are kind of just whatever. So let's start with spiral galaxies, and why do spiral arm galaxies look the way that they do? Most of the material in spiral arm galaxies kind of revolve about their cores, about their centers in a disk. So why do they look like that? Well, if we want to think of a couple of things that have that kind of shape, think of like a pinwheel and like a ninja star, right? A shuriken. What do they have in common? They rotate, right? Windmills too, right? They all rotate, and so they kind of have that, that spirally appearance. And that is why spiral arm galaxies look the way they do, because they rotate about their center of mass all kind of in the same direction. Except near the core, of course. Near the core, there's like a central bulge because the stars there are kind of moving in more random directions around the core. So why do elliptical galaxies move the way that they, or look the way that they do? Because they're moving around the core, and you know, not like in spiral galaxies, they're kind of moving around in lots of different directions. But why are they elliptical and not spherical? Because if they're moving in truly random directions, they would be spheres. However, they move in some directions more than others, and sometimes in very, very complex orbits. And elliptical galaxies, of course, don't follow any of these rules. Other differences, of course, spiral galaxies are hard to see through because they have lots of gas and dust and stuff in their disks. And so they kind of occult and hinder the passage of light through their disks. Now I know what you're saying, right? I just said cold. And according to the Stefan-Boltzmann law and Wien's displacement law, where you can just kind of look at the color, yes, gas and dust is generally pretty cold out in space. And on the other hand, elliptical galaxies are usually much hotter, right? Spiral galaxies kind of have like a net rotation, and so all the gas settles into a disk, not terribly unlike accretion disks are forming around protostars. Because elliptical galaxies don't have net rotation, their gas doesn't settle into a disk, and so it doesn't get cold, right? The cold gas can't collect anywhere. Now, if you look at kind of the color profile of spiral arms, right, you can tell that star formation is happening in spiral arms and not so much in elliptical galaxies, right? In elliptical galaxies, the temperature is kind of too high, the gas doesn't settle. But in spiral galaxies, and I know this is maybe a little counterintuitive because blue is a hotter color, and there's definitely blue in the spiral arms, right? But what that means is that the gas and dust settles enough that stars can form. And remember, blue stars are the brightest and hottest, and they're so much brighter that they kind of outshine all of the other stars in the spiral arm structures of spiral arms and barred spiral galaxies. Interesting stuff, right? And it's true, of course, that most stars, especially on the main sequence, are red, but even though the blue ones are so few in number, they're so much brighter that star formation happening makes the spiral arm regions blue. Anyway, we'll come back to that. The luminosity of galaxies are also different. Spiral galaxies aren't usually quite as bright as ellipticals, both because of the increased temperature and because of the increased surface area. You're talking about a three-dimensional object as opposed to a two-dimensional object. And that's, if you want to go back to the Stefan-Boltzmann law, which object is brighter, the small stove or the large stove, right? Even if they have the same temperature, the object with the greater surface area is going to have a greater luminosity, right? It's going to give off more light. And so, while there are bright regions in spiral galaxies, and some elliptical galaxies are dimmer, the brightest galaxies are elliptical galaxies. But overall, the size depends on mass, right? Well, yeah, more massive galaxies have the potential to be brighter, right? More mass means more stars means more light. And so if we wanted to compare galaxies to, say, the Milky Way, some galaxies are larger than the Milky Way, brighter than the Milky Way, or smaller and dimmer than the Milky Way. And that's kind of the benchmark that we use. There are only two kinds of galaxies, essentially. There are ones with more than 1 billion solar luminosities. We call those giant galaxies, or just galaxies. And then there are ones that are less than that. And galaxies with less than a billion solar luminosities are often called dwarf galaxies. So you got dwarves and giants, nothing in between. Anyway, back to spiral arms. Spiral arms are kind of interesting because they're made out of largely, cool gas and dust. But we know that star formation is going on there. And if we think back to our picture of star formation and the structures in the Eagle Nebula, we call those the pillars of creation. Um, Irregular galaxies can also kind of have star formation regions because, they can have bunched up gas too. But the gas and dust that settles in these spiral arms, they make nebulae, molecular clouds. And in these clouds, of course, you can have free fall contraction and eventually star formation. Interesting, right? Now, why are there spiral arms? We mentioned briefly that there's rotation, right? But what makes the actual arm structures? And as it turns out that the arm structures are not actually really structures. There's nothing holding them together. The reason that we have what look like spiral arm structures is that essentially a bunch of matter can kind of get bunched up together, kind of like a traffic jam, right? A traffic jam isn't held together by gravity or by, cars getting linked together. It's not like a train, or a bunch of trains all hooked together or something weird like that, right? There's nothing keeping a traffic jam together other than the fact that, the cars don't want to crash into each other. It's a little bit different, obviously. The stars aren't trying to keep from crashing into each other. Instead, gravity is kind of briefly pulling them sort of together, right? But basically the material just kind of gets bunched up. Stars are kind of making their own paths. Stars further out from the core of a galaxy are going to take longer to go all the way around. And so spiral arms over the course of time disperse and reform elsewhere and whatever. Long story short, spiral arm structures aren't actually structures. They're more like traffic jams. Just kind of circumstantial happenstance. Gas bunches up like cars in a traffic jam. Now, gravitational disturbances can cause a spiral arm to form. However, so can, star formation and stellar winds and supernova events, things blowing up, right? Those can cause gases to compress into greater density and so on, and that can cause more star formation. In any case, in order to try to estimate the mass of galaxies and how the mass is distributed in a galaxy, astronomers have tried to sort of total up what we call the luminous matter, the matter that actually gives off light inside a galaxy. And in order to do that, we compare what we call the rotation curve of a galaxy. It's like this. If you're looking at a galaxy that's way far away, right, and you can see that it's like a spiral galaxy, you can look at one side that's coming towards you and one side that's going away from you. And you can measure a star on one side, right? If it's coming towards you, its light's going to be blue shifted. If it's going away from you, the light is going to be red shifted, right? And you can measure what the red shifts are at varying distances from the galactic core in order to try to get a sense from the difference of these red and blue shifts how fast the galaxy is rotating. Pretty straightforward use of the Doppler effect, right? Using the differential Doppler shifts in order to try to discern the relative velocities of these stars in these rotating galaxies. Now, originally, what we wanted to try to do is match those up with Kepler's laws of planetary motion. And if you think back to the second and third laws, right? Obviously, a star that is farther out from the galactic core, we'd think that would move more slowly, right? It would have a greater period of revolution about the galactic core and so on. But it's actually not the case. All of our data suggests that essentially stars kind of all the way out to the edge of a galaxy at the edge of these spiral arm structures move just as fast as stars way in close. And that's kind of interesting, right? Now, our basic assumption that stars are supposed to move, faster if they're closer to the galactic core and slower if they're farther away is because we're assuming that the major gravitational interaction would be between a star and this hypermassive object, this galactic core. But that's obviously not the case if stars out of the edge of a galaxy, way, way far away from the galactic core, are moving just as fast as stars that are sort of really close to the galactic core. And so there has to be some other kind of gravitational interaction that's causing stars all the way at the periphery of a galaxy to move just as fast as stars near the core of a galaxy. So what is that? What is causing these stars to accelerate the way that they are? What is causing stars at the periphery of a galaxy, way out here, way, way far away from a galactic core, to move just as fast as stars that are really close to the galactic core? The answer is we don't know. This is called the dark matter problem, because it's a problem that we haven't solved yet. We know what about maybe 90% of the matter in galaxies is not. Let me rephrase that. That means we know maybe up to 95%, between 90 and 95% of the matter in a galaxy is stuff that we don't know. Or, if you want to think of it this way, we know about 5 to 10% of the matter in a galaxy. We know the identity, or what about 5 to 10% of the matter in a galaxy actually is. That's the luminous matter, stars, black holes even. And so we know about what 5 to 10% of matter in most galaxies is. But for spiral arm galaxies and barred spiral galaxies to move the way that they do, with these velocities, pretty much flatline all across the board all the way out to the end, how can this matter possibly be distributed? And it turns out actually that elliptical galaxies, we think the mass distribution is got to be about the same. And in order for stars all the way at the edge of a disk of a spiral galaxy to move like they do, and stars pretty much everywhere in an elliptical galaxy to move the way that they do, there essentially has to be a tremendous spherical halo around a galaxy filled with this crazy dark matter that we don't know what it is, in order for stars to move the way that they do. Like I said, elliptical galaxies are pretty much the same, but it's a little harder to get a good grasp of the relative red and blue shifts if not everything is moving in a disk. But, we just kind of compare that to stars in the core and whatever. One of the things that we as a species are pretty good at is signal processing. And so we've kind of been able to figure out by comparing redshifts and blue shifts how stars in elliptical galaxies move. And they're kind of the same thing. They move at basically the same velocities all the way out to kind of the edge of the galaxy. And so that begs the question, what is dark matter? Well, long story short, we don't know. We have several objects that we think are good candidates, but the truth of the matter is that we don't know what they are. We don't know what dark matter is. That's why it's the dark matter problem and not the dark matter solution or whatever, right? We don't know what dark matter is. Like I said, there are a few things that are candidates. We came up with the idea that there could be massive objects out in the halo, in the dark matter halo around the Milky Way. Things like burnt out stars, black holes that were, like that had lost any kind of gravitational connection with the bodies around them, white dwarfs that burnt out. Red dwarfs are T Tauri stars that are too small to actually become stars, massive objects, but not big enough to actually become stars and leave behind stellar remnants like white dwarfs. Things like that. Now, if you have massive objects, large, objects, things that are bigger than, asteroids or whatever, right? If you have a bunch of these massive objects, what we call massive compact halo objects, MA for massive, C for compact, H for halo, and O for object, we're using the acronym MACHO. These massive compact halo objects, these MACHOs, because they are a lot of mass in kind of like a small region, they should exhibit gravitational lensing, which was, you remember the Yo Mama joke, your mama's so fat you can see what's behind her? Because when you have a very massive object, the light should curve around the gravity well, right? And so what we did is we looked for gravity wells out kind of outside of the disk of the Milky Way, just to see if we could see kind of random gravitational lensing to try to find these massive compact halo objects. And we found some, but not a lot, not a tremendous amount. We essentially found enough that in any theoretical model, it could predict no more than about 20% of the missing mass. So not a lot. So what else could it be? Well, we thought that maybe instead of these massive compact halo objects, what if it was just bunches of particles that were kind of spread out all over the place? And we decided to call these weakly interacting massive particles, WIMP or WIMPs. And I'm not really sure if they decided to call that in response to calling the other objects machos, just so we'd have machos and wimps. But for whatever reason, yeah, wimps and machos. A couple of examples of wimps could be things like neutrinos. And that's a possibility. Neutrinos, of course, are difficult to track. They don't like to interact with matter. There are a couple of other small, low-mass particles, which could also possibly be the answer, but suffice to say that that is a very, very difficult theory to test, because neutrinos are incredibly difficult to find. We've only been able to find the ones that actually go through the Earth, and even that is kind of an involved process, right? It's not easy, it's very difficult. So suffice to say, we know that dark matter is there, but we don't really know what it is. And even in our theoretical models, there's still something missing, which is why we call it the dark matter problem. Okay, that's enough for today. That is essentially galaxies. Oh, you know what? I neglected one thing. there's this funny thing that we call a tuning fork diagram. And this tuning fork diagram has like barred spirals on one tine of the tuning fork and spirals on another tine of the tuning fork, and then there's like elliptical galaxies on the what would be like the handle of the tuning fork. And essentially that's just a classification scheme that we use to classify the visual appearance of galaxies. When I started first learning astronomy, and that was only a few decades ago, we used to think that that was like a pattern for a path for the evolution of galaxies. Because we used to think that spiral arm galaxies would collide with other spiral arm galaxies, and those would make elliptical galaxies. But we know now that that is not so much the case. Because all of the modeling that we've done to show what's going to happen when the Milky Way collides with the Andromeda galaxy, we're going to collide and we're going to end up with essentially another spiral arm galaxy. Okay, if you have any questions, please get a hold of me through the normal channels. If you have any questions at all on, I know this is kind of a lot of material, especially when we're talking about the dark matter problem, please just get a hold of me. I hope you've enjoyed this lecture as much as I have enjoyed giving it, and we'll see you next time.